right, let's see what you got going. Oh, we can roll into this slowly. A few minutes to go. So. Another Red Bull deal, I guess. Does anyone here drink that stuff? Never had that. What is it, just sugary Coca-Cola? Pretty high. You can see the curvature of the Earth. I'm not sure. Maybe 100,000 feet. I'm not sure. Oh yeah, 128K, 128,000 feet. A leap of faith. Looks like he could do a good job falling out of the plane. So yeah, I don't know. I don't know what the. I guess the point was to be the highest free fall jump. I suppose. I'm not really sure, but it certainly was. So well, we've seen that one before. Actually, yeah, we have seen that one before. Some of the more mundane things that you use external flows for, not very different from Felix Baumgartner, I guess. Is it actually working? That's a little bizarre. Should I refresh it? What's going on? Yeah, so what should I be doing? Anyone? Excellent. Maybe. Apparently not. As well. Okay, one of the more mundane things that we use external flows for is getting the gradation of fine-grained soils. It's difficult to sieve them, to have a sieve that's small enough mesh to get it through. And so one thing you can do is you can put it in water and let it settle, and you can calculate how long it takes to settle in a graduated cylinder. And the rate at which it falls is proportional to the diameter of the particles. So, let's see if this works. Yeah. And this is just interesting to watch, I thought. Yeah. Ink falling in a blob of water. So, the objects can be solid, but I think, and I don't know whether this is I think some of these are observations, and some of them are models to match those observations. So in the same way that you can imagine a hailstone dropping through a cloud, and the way that hailstones are generated are the updrafts in clouds push them back up, so they go through multiple times, and a nucleation happens on a small ice crystal that grows and grows and grows. Yeah. So, but you can also imagine a dense fluid dropping through a less dense fluid and doing some strange things. So quite interesting behaviors. I'm not sure what causes it to do that, but it's kind of curious that you can match it, not just the observation, but you can match it with some kind of simulation. I'm not sure what the other, I didn't look at them before, not sure what the other ones are. Right, so, yeah, quite interesting. Yeah, fine. So things don't have to. Oh, are these solid particles? No. there's still fluid. So anyway, so the things we're kind of talking about are related to that. Was there other things? I guess there was one other thing I thought was interesting. That's not, well, this you've seen before, and is sounds spooky. So galloping Gertie, right? You've seen this before, must have seen this in high school physics classes. Again, it's an external flow, and we know, we've talked about the reason for it before, is that wind blowing above and below the deck acts a bit, not so much like an airfoil, but on the trailing edge, where if it's blowing from left to right, on the right-hand side, you get these vortices shed successively from the top deck and the bottom deck, so-called von Karman vortex street that plucks the bridge at each exiting vortex. And if that plucking of the bridge is in concert with the resonant frequency of the bridge, then the amplitude of the bridge builds, and you all know the outcome of this. I think there was a dog in that car, unfortunately, but that perhaps was the only casualty. Very matter-of-factly walking across the bridge. I think I might be running, and then ultimately pulls itself apart and drops into the Tacoma Narrows, right, in Seattle. Yeah, so you do that once, and then you learn from it, and then you figure out how to guard against it, I guess. One more thing was this vortex.
Hey guys, do you understand that concept? I've been trying to save you.
No, it doesn't. Well, how do I go back? I could reload these, I guess. I don't know how to go. Fine, I'm not. Oh, let's go back here. Yeah, fine. Always a happy ending, apparently. And, well, another external flow, of course. Wind turbines, airfoils on planes are the same. You see the trailing flaps at the back. This shows a vortex rolling off it. We looked at wings on a Piper Cub on Monday, looking at the high pressure underneath, low pressure on top, the fact you have winglets that stop flow around the wing per se, and it's just here that you can see it by this condensation trail that comes off it. So it's the 757, I think. They changed the separation in landing distances when, this is LAX as well, and I think it was at LAX, or perhaps it was Orange County. 757 was landing and an executive jet was landing behind it, and the executive jet just got slammed. It was only perhaps a mile behind it, but the vortices were trailing and still left in the air, that they slammed the jet into the ground, and it was a crash. Some people died as a result of it. So they changed the separation to 5 miles behind 757s, I think. And what else was there? Oh, yes. The other thing was this. It opens. And again, you see, you need more lift when taking off, I guess. And so you have these leading edges. Also, there's a whole architecture at the back of these trailing edges that extend. You hear it when you're landing, right? They're extended by screws that push them out, so they're quite stable. And so these provide an extra shape to the wing to give you a bigger curvature, so a longer distance to travel on the top. And so that means that you have to speed up if you're going to join the airflow at the back end of the wing. That's kind of how an airfoil works. And so you need the extra lift for takeoff out of O'Hare in this particular case. And then once you get airborne, then you don't need that lift anymore, and you'd much rather have a wing that's aerodynamically efficient with not very much drag to it. And so the leading edges get retracted, and then you travel off to wherever you're going. So this is a 747 sitting up in the bubble in this particular case, I guess. So that's that. So that's what we're chatting about. So that's our preamble. We won't meet on Friday. I'll post that these 3 classes are all extra credit classes. You'll get extra credit if you sign your name up, if someone wants to put a sheet of paper around today as well. Others who don't come will have to do the quizzes. Not that they're particularly challenging, I don't think. I'll mention that probably in the weekly email, so I'll keep the Mondays ones. Won't affect you. If you didn't do the Monday ones, those will stay open till Monday, I guess. So it gives a chance for people who weren't here on Monday and who aren't religiously following these recorded videos today, this statement now, that they'll know to be able to watch those. So that's what's going on. Midterms next week, I think you know what they are in terms of materials. One on energy equation, the Bernoulli energy equation, not the enthalpy energy equation. One on Buckingham pi, and one on pipe flow. They are all retread questions. So if I were preparing for it, I guess I'd know the previous examples dead to rights. I think that's the easiest way to prepare. So they might not be verbatim, but they're based on those. So if you understand how to do those, that's the best way to prepare. Other than that, you have the review session recorded. I'm not sure what else. Anything else? Same format as before in class. Yeah. So anyway, good luck on those. On this, we were talking about lift. I remembered that one of the things we didn't do, which maybe you'd do in 2 seconds when we talked about the last part of pipe flow, we skipped over flow rate measurements. And so only to say, not related to anything related to tests or anything. So don't read anything into this. We just didn't cover it last time. If you want to measure flow rates, the easiest way to measure it is by measuring pressures, because it's a solid state measurement without any moving parts. And so the way to do it are using orifice meters or Venturi flumes. And so they just rely on the fact that you constrict flow. As you constrict flow, it accelerates, and therefore you get a pressure difference. We've derived this expression before, and I guess this part only talks about what the correction factors might be for these calculations. So if you want to get flow rate as a function of pressures upstream and downstream, upstream and at the orifice, then you just correct it by some magnitude. And depending on how disruptive the plate is, the more disruptive the correction factor might be larger, typically a function of Reynolds number, and the less disruptive in terms of flow, then the correction factor might be almost trivial, right? These are almost 1, and so it doesn't really change it very much. And the most smooth transitions, of course, are Venturi meters, which are just a very smooth narrowing of the flow before it goes downstream. Other ways of doing this, I've never quite worked out how the mechanical tire gauges work. You put it in a tire, measures the pressure by a little stick that comes out. It may be related to this. You could imagine that if you have a bead in an airflow, if the airflow container, the pipe widens, then you know from continuity that if you take sections across this, the velocity will be slower here than it is here, just from continuity. And so there's some balance point at which this weight would be held by the flow, killing the velocity of the flow by a pressure applied at this bottom end, and also on these flanges, I suppose. And so the height to which this would rise would be some measure of the flow rate, which you could calibrate, of course. You could imagine impellers in tubes, where if you can measure the rotation of this, I presume you measure the rotation of this by a magnetic sensor. So turns. You could put a coil around it, just like a small electric motor or a generator. You could measure the voltage that you produce from this, or you could measure the number of clicks that you get by it turning in the flow. Clearly not a solid state measurement, because you have moving parts. For those of you who will work with drill holes, a typical way of going back into a petroleum well or sometimes groundwater wells is a so-called spinner log. When we talked about substantial derivatives, uppercase D, T, dt, D temperature, we talked about putting a sonde down a borehole and then retracting it. And typically spinner logs are just a sonde that's put down the borehole. It has a small impeller on it, and the impeller gets turned as it goes through either stagnant fluid and then brought up through the same stagnant fluid. If the fluid is flowing, then you get a different velocity profile of the impeller on the way down than you do on the way up. And so you can tell from that if some water is going into the formation or coming out of the formation in the hole. So it's just exactly the same as this. And I don't know how these work at all, but nutating flow meters, there's a little, I had a video, I don't think I showed it in class, but it's something that flips from upstream to downstream and also almost gives a measured volumetric flow rate with each container that empties as it goes downstream. And these are the gas. You see them on the rental properties. You see these gas measuring devices for natural gas. They have bladders inside that physically measure a very accurate volume of the gas by having this bladder change shape as gas flows through it. So it almost meters the gas in bucketfuls of gas as it goes through. So I have no idea how they work, and I don't think we need to look to understand that, but different ways of measuring flow velocities in pipes, particular case. All right, so, well, we're a quarter after already. We are talking this, okay. So, on to the business at hand. We're talking about external flows. I guess last time we talked about summarizing where we got to, so I won't do that again. But what we might do is start from talking about lift and drag. You remember that we mentioned that they are the same properties, but drag is measured in the direction of flow and lift is measured perpendicular to that direction of flow. They emanate from two responses, one due to pressure and one due to viscous drag, due to viscosity, shear forces. And we can define that behavior by looking at a surface on which those two forces are acting, either pressure or viscous forces. And if we want to resolve them in the direction of the drag force, which would be in this direction, actually in the opposite direction, it occurs against the flow, is that we can calculate the individual components of the forces that are acting on a small length of that surface, inclined at an angle theta, and where the shear force is parallel to the surface and the pressure force, as we know, is always perpendicular. So if we look at the shear force and resolve it along the direction in which it is applied, we can also define what that magnitude is in the direction of the flow, which is what we want to get. And so the components would be a shear force as drag. And if you look at the normal pressure and its component also in the direction of flow, then this would be equal to the pressure times the area of which it acts, dA in this particular case, times the cosine of the angle at which it acts. And so if we take these two components and add them together, then we get this relationship. We can just calculate the integral of the forces acting in the direction of the flow direction, which is horizontally here, and it's the pressure times this times the length over which it acts, and the shear force times area corrected for the inclination relative to the downstream velocity. So we can use these to be able to, if we have, and I said last time, it's kind of esoteric because we need to know a solution for both the shear stresses on the boundary and also the pressures. And so if we have those, we can actually do that. And so we do have some cases where we do know that. And so this is one of those esoteric cases. So if you have a plate, which is an airflow going against it in English units, you can imagine that you might have a solution for the shear forces which are applied on this. And if the shear forces are due to this boundary layer, the solution for this is equal to a constant multiplied by a length downstream. So 1 over, so it's 1.24 times 10 to the minus 3 times x to the minus half. This is 1 over, right here. And so if you wanted to calculate the force that you have to apply to this plate to keep it in place, then you can do that just by summing the contributions of this force. So I don't know that they show it. But if you take this relationship and look at this equivalent term here, you can merely evaluate that by taking, in this particular case, this, the area over which it acts, and we have this both on the top and the bottom. So the angle here is going to drop out for the shear force because it's 90 degrees, right? The normal to the surface is 90 degrees. And so if we know the magnitudes of these stresses, we can calculate it. And is it written at the top or is it written down here? So this is it here. So if you want to integrate those, it's going to be the behavior on the top plus the behavior on the base. They're identical because it's just the symmetry of it means that they are identical magnitudes. And if you substitute the terms into this expression, then this would be this relationship. This is tau w. It's integrated along the length of the plate. It's 4 feet long. So this would be x equals 0. This would be x equals 4 feet. And the plate would be 10 feet into the page. And so if you sum, this is 10 feet. And so the rationale of summing those components is that this is the magnitude of the shear stress, this is the width into the page, this is the length along the fin that you have to integrate it, and you're integrating it from the front end of the plate to the back end of the plate, and you're doing top and bottom. And I haven't checked this result, but if you integrate that, x to the minus half should be, what's x to the minus half? Should be something like x to the half times 2. Is that right? So x to the half becomes x to the minus half, and 2 times a half gives you this, right? So the integral of that should be just that. And if you do that and substitute it between those limits, and then you should get that. Likewise, if you wanted to calculate the lift for that particular component, you could surmise that there wouldn't be any. If the pressure is 0 at everywhere along this length, then there would be no net lift, right? But even if there was a net pressure, you could imagine that it would, on the top it would be acting downwards, and the bottom it would be acting upwards, and so the net effect of those would cancel out exactly, and so there would be no net lift. You can turn the plate to face the flow that's hitting it, and then in this particular case the solution is given by this. On the front side it's drafted out by this near parabolic, I guess it is parabolic form on the one side, and on the trailing side it's a suction, a negative pressure, So this would be negative gauge pressure. So these would be additive because this is acting perpendicular to the plate going downstream, and this is acting, sucking the plate going downstream also. Again, for the shear stress distribution, you could imagine as the flows go and separate around the plate and do this, that any shear stresses from this would be also symmetric about the middle line, and so there would be no net lift, but there would be pressure drag on this. And so I think that's what's done in the next portion. So you could imagine that the lift from the front and back, the distribution of shear stresses on the front and the back would directly cancel each other. They'd be equal to 0. Right? You could imagine some kind of, I don't know what the shear distribution would be, but if you had a plate like this, you can imagine you might have a shear force here, and you might have a shear force here, and you might have this and this. So the symmetry of these two on the back are going to cancel each other, so there's going to be no net component from these. And the symmetry of these on the front are going to cancel each other. So individually, you'd expect that these components would also be equal to, the summations of these would also be equal to 0, right? Because you're not just the magnitudes of the shear forces, but the summations of them. And the drag would be the pressures acting on the front and the back. And so if the frontal pressure is equal to this term here, and the rear pressure is equal to this, which is just a constant, doesn't change with y. So this is just a constant. This one is negative because it's below gauge pressure, but negative minus a negative because we're resolving in this horizontal direction, just from the sign convention. So this becomes a positive because of these two components here. So these become additive to each other, as you'd expect just from the geometry that we have. So this is a function of y. Y is the direction from the midpoint upwards and downwards. So the limits of integration are between -2 and +2, the heights of the plate. It's just the same plate turned on its side. And if you integrate those, you end up with some magnitude, which I haven't checked this either, but you'd get this. You'd have to integrate this y squared term dy. And so it'd be y cubed, so integral y squared dy, I think is equal to a third y cubed, right? And you subtract these when you differentiate. So you get this. So that's it. So the problem is, of course, that you need to have a solution for the pressures and the shear stresses to be able to do that, which you don't always have. And so that's one way to be able to make those calculations if you have them. What else do we know? So a visual, I guess, of what's going on is that you expect them to be two components that are given in this expression. So if you want to calculate the forces, you have it from an integral of P dA plus an integral of tau dA plus some other terms, right? So these represent the two origins of these forces. One is due to pressure, the force on the side of the truck on San Francisco airport apron, which is just by killing this velocity at this stagnation point and then pushing. And then the effects of the drag, the shear drag on the side. And we've also mentioned last time that just like in pipe flow, we expect these behaviors to be different at different flow velocities. And so we'd have to be mindful of the fact that although these shear drag and pressure drag will always act, the relative magnitudes of them might change depending on the flow regime we have. And typically the flow regime will be defined in terms of Reynolds number. And so we can go back to that kind of idea. and we would expect that as we go from low velocity flows, we have laminar flow where the flow hugs the cylinder, and therefore it exerts shear stresses on that cylinder, both top and bottom, always in the plane of the surface. And as the velocities increase, then the flow separates at the back, and we get these wakes forming. And indeed, just like Tacoma Narrows, you get a vortex shed from the top of the sphere, and then alternately one shed from the bottom. So if you look downstream, to take a picture in time, you'd see a continuing up, lower, upper, lower, upper, traveling vortices going downstream. And I guess to be efficient in aerodynamically, you'd prefer to have flows which don't separate, and that's why people wear these helmets in the sprint in the Tour de France, which are surprisingly blunt on the front, but tapered at the back, so you avoid the separation and therefore the drag that occurs. So it seems clear that we want to know what the Reynolds number might be in those particular cases to be able to classify those flows. We can also go back, I guess, to dimensional analysis and think about this. And if we imagine these systems, we're going to classify them in terms of a force that we want to apply. And this force is going to be equal to the drag force, which I'll call Fd. So if we want to be a cyclist pushing with force F, we're resisting this drag force. And we could get this drag force from what we did with these closed form solutions, because we know what the net force is that's applied on this structure, or we could measure it in the wind tunnel. So we can try and get the minimum number of variables to do our experiments. So if we look at this geometry, you could imagine that we can classify it in terms of a drag force that gets applied on our structure, something about the geometry of our structure, which would be perhaps the area, and the area would typically be the planiform area. So this would be the frontal area, if you like, looking at this airfoil. Just like our characteristic dimension for a pipe was its diameter, for a sphere, I guess the planiform area would be a circle, right? No, I didn't want to do that. I wanted to. So this would be the frontal area. This would be also an area A, right? If you imagine looking at the sphere from upstream, this would be the cross-sectional area. This would be the cross-sectional area of a. This could also be, I guess, almost a circle as well, right? So some geometric component. We want a far field velocity and the characteristics of our fluid. So from Buckingham pi, we know that the variables are 5. We know that mass, length, and time. Mass is in here, time is in here, in velocity, and length is in here. So we have all three of those represented. So that's 3. And if we subtract 3 from 5, it means that this is given by 2 pi groups. So if we choose some repeating variables, the repeating variables have to have all the terms of mass, length, and time in them. So length, time, and mass are included in these. So we have 2 remaining non-repeating variables, which would be viscosity and the drag force. So combining the first, I won't go through Buckingham pi, but if we did that, we'd end up with something with an area to the square root, which is really a diameter, some kind of characteristic length. And so this is clearly a Reynolds number, inertial to viscous forces, density and viscosity. And if we throw in and do Buckingham pi on it, or just do it by inspection, we take the drag force, then we get a different number in it, which is an Euler number, right? We could also write this as if FD over A is equal to a pressure, then this would be a pressure divided by rho V squared, which is equivalent to an Euler number. So exactly what we knew before. We have to get the flow regime right, we have to have kinematic similitude, and if we do that, then we make sure that we're looking at the right flow regime where we are. We measure the pressures or forces applied to this structure. It could be the force, right, if we use this expression here. And from that, we can get an Euler number at that particular Reynolds number. And then we can use that to define lift and drag coefficients. So that's how it's done. I skipped through to this, but let's do this anyway. So this is going to look exactly like what we had before. Hopefully, I think it's actually in the next class. A long way down. I did this. This is what I'm looking for. So you can imagine taking a sphere, putting it in a flow, measuring the force that you have to apply to keep it static, having an impinging velocity on it, having a particular diameter for that. I guess I'll use lowercase d because I don't want to confuse it with squirrely d, which is the drag force. So this is what we would refer to also as drag force. And so you measure the force for a given velocity and the fluid's going past it at some given viscosity, density, and viscosity. And you do it at some velocity and you get 1 point. You do it at a higher velocity, you get another point. You do it at a higher velocity, etc. Because this coefficient of drag is equal to squirrely d over, I think it keeps the half rho v squared a in it. So I think a would be some characteristic dimension, so it would be pi d squared upon 4. And so that's it. So if you don't have a solution to be able to solve it from the integral equations we talked about, which is usually the case, then you can get it from just doing experiments. And the minimum number of experiments you do would be this. So the utility of this is that now you know the coefficient of drag at all Reynolds numbers. And so if you want to be able to calculate the bottom line, even though we're not there, if you want to be able to calculate the terminal velocity, you could think of Felix Baumgartner. He's traveling at velocity v, or you could think him as in the wind tunnel static and the air coming past him at velocity v. And then you have a weight of a structure, you have a drag force acting upwards, you have a buoyant force equals the volume of the sphere multiplied by the density of whatever the fluid is that you're displacing, because this is solid. And then you can just do a force balance, that W equals squirrely D plus buoyant force. You know the volume of the sphere, you know the density of the fluid, you know the weight of the person, so you know this and you know this, and so you can write that squirrely D is equal to you can rewrite this expression as D being equal to CD times a half rho v squared times A. So you absolutely, I guess we're jumping the gun. This is just how it would be done. You absolutely know the buoyant force from the volume. You absolutely know the weight. You know this as a function of velocity. So if you set these equal to each other, the only unknown you have in this equation is velocity. If you know you're turbulent, you know that the coefficient of drag is something like about 0.4. And so if you know what this is 0.4. Then the only term you have to calculate is the velocity. So you need to get that. And so you can solve for terminal velocity. This turns out to be 200 miles an hour or something like that if you do this for air. So I guess that's kind of impromptu. So that's where we ultimately will go. And so the desire is that we could do some experiments to be able to measure exactly what those coefficients of drag are. So we can define two of them. One that's measured perpendicular to the flow. And so if the flow is in this direction and you have some kind of structure in there, then not surprisingly, this squirrely L is this, and squirrely D is this. And that we expect that we have these values available to us from charts or from some kind of reference table. So long as we can get these and that they're at the right Reynolds numbers, then if we know what the forces are that are being applied in our system, the weight of a guy dropping out of a balloon-carried pod, or a grain of soil dropping through water, you can get the velocity from that. If you measure the velocity of a grain falling in water, then you can solve for the dimensions of the grain. It's just a different way of doing it. But this is what external flows are all about. Bless you. So lift and drag coefficients. And so these would automatically, I guess I can draw that. These would automatically include the two components we talked about. So if this is coefficient of drag, which is also really just an Euler number, and this is Reynolds number, then we know that from what we just looked at, this is our behavior, right? This is, whoops. So we know that within these regimes, what we have is laminar, a transition to turbulent. And so in laminar flow, if we drew out what it looked like, then this particular flow would be like this. So these are the difference. So this would be pressure drag. And this would be viscous drag. So this would be the effect of what we call tau, which is a function of viscosity. And this would be P, which is a function of fluid density, right? Get squirted by a fire hose firing air or water at you, you'd feel the difference if it was water because of its density. And so for the same velocities. So that's really what it is. So we need to make sure we're in the right regime. And if we are, we'd expect to have the right solution when we calculate what the drag coefficient is. If we know what the drag coefficient is, we can always calculate the forces that are applied. And depending on the problem we're solving, if we know the weight of the particle and its geometry, then we can solve for the velocity. If we measure the velocity and want to calculate the dimensions of the particle, then we can solve for that as well, either way. And so that, I suppose, is a manifestation of this picture, right? We'll always have pressure drag, we'll always have viscous drag, but the magnitudes of their proportion will vary based on the flow regime. And so I think that's what is illustrated in these figures. So these are different, these are for the plate problem that we were looking at before. They're for different Reynolds numbers. The Reynolds number is defined in terms of a velocity, a length, divided by a kinematic viscosity, which is the same as a velocity times a length times a density over viscosity. So kinematic viscosity, which is this nu, is just equal to density over viscosity. Just a standard term that's used in fluid mechanics, I guess because it makes one less term in the Reynolds equation. I'm not sure why it's used. And so if you look at the far field velocity, too much whiskey. Far field velocity, different from pipe flow, right? In pipe flow, we're interested in the effect of the pipe on the velocity. In this, we're interested in the velocity on the forces on the object. It's kind of backwards. So if you get to the far field, the velocities don't change very much. But close to the plate, it's controlled by the zero velocity at the wall that we get because the molecules of air or water are attached to this plate. And so you can imagine a zone. This stippled zone is just the area where the velocities are different from the background far field velocity. And so for laminar flow, because it's viscous flow, it goes slowly to the background velocity as you get further away from the plate. And this is a Reynolds number of 1/10. So this is laminar flow. So the flow is actually hugging the plate. As you increase the velocity 100-fold, I guess, 0.1, then it starts, this stippled area gets reduced. It gets much more quickly to the background air velocity as you go away from the plate. And when you get to a very big Reynolds number, then you get exactly a thin boundary layer. I guess this isn't quite the case. It's actually 0 as it goes onto the wall here, but it's a very thin zone. And because it goes quickly to the background velocity, this is quite an efficient way to get through the air, because you're not dissipating all of the energy in your system by this viscous, it's like a pack of cards, pushing a pack of cards over each other. All these little slithers of air are sliding past each other at different velocities. And so since you know that the shear stress is equal to the viscosity times dV x dy, this is the x direction here. So this is the velocity in the x direction, but it's changing as you go in the y direction. This is using up energy in the system. Likewise, if you look at a cylinder or a sphere, cylinder in this case, into the page, same behavior. If you looked at the velocities coming out from here, they would look like this, to this magnitude. If you looked at them on this lower one as they go out, they would go like this, and then this. So a very narrow region in by the wall in which you're dissipating energy. So it's the reason for golf balls being dimpled is that the Reynolds number at which you go turbulent is controlled by as you know, is controlled by roughness for pipes. Same for structures. So if you imagine this golf ball, not a very good golf ball, having some kind of roughness on it, the dimples on the ball, is it goes into the turbulent regime where this is the flow regime at a lower velocity than it would do otherwise, and therefore it goes further because there's less force that's applied on it as a result of that. And I think the last thing I was going to chat about was this. So this is Tacoma Narrows. And so this is, you can imagine this being the deck of the bridge that's suspended by wires, cables, I guess. And you have flow across this bridge, and it breaks to do this. At very low velocities, it'll hug the bridge and be a creeping flow around it. As you increase the velocity, then you'll get a vortex shed off from the top, and then one shed off from the bottom, and they'll move downstream like this. You could imagine this as being an equivalent sphere of some diameter, and if you take a snapshot in time, this was done 5 seconds ago, 3 seconds ago, 1 second ago, and they just move downstream. But as this gets shed, it gives a little pluck to whatever this structure is. It happens to be quite a stiff structure. It's the deck of a bridge, but it's not infinitely stiff. And so just like plucking a guitar string, if you pluck it, continue to pluck it at the frequency that this long bridge wants to vibrate at, the vibrations will slowly build. And apparently the frequency of these is equal to this Reynolds number, which would be defined in terms of, I'm sure it'd be defined in terms of a velocity, a flow, a diameter of the bridge, and a density of the air divided by the viscosity of the air. 1 kilogram per cubic meter, 10 to the minus 5 Pascal seconds. And so this is a non-dimensional number. Frequency has to be in units of 1 over time. So this is velocity, which is length over time. Diameter is length. So this is in units of 1 over seconds. So if the resonant frequency of your structure is equal to whatever this frequency is, then it will start building up, either to pull itself apart or to make it uncomfortable to drive across the bridge in the lesser case of that. And that's it. That's all I have. So that's it. We'll talk. We won't talk. It's online on Friday. The class on Friday is talking about the kinds of things we broached on today. Just some examples of calculating how a hailstone gets lifted in a cloud, what the terminal velocity of a person is, just by using these expressions for lift, just as we did here. And then midterms next week. So, good luck in the coming hour. Have fun with Nelson stuff. You can contact me an email, or I'll be around today as well if you have questions about tests. The projects are due the Sunday before Thanksgiving, and it's a softish deadline, but it'd be good to get it in on time because Matt will want to grade it. That's about it. Good. Thank you. Great. Good luck with Nelson's class.